So now we need to find out where does this my data 0 getting set to the wrong data. So again, we're going to use the last command, and we'll just type in my data 0 here, and that's going to wind back to where it's set. Hello everybody, my name is Jonathan at Lightblue Logic, and today I'm going to be talking about using time travel debugging for SystemC. SystemC, for those who are not so familiar with it, is a set of C++ libraries enabling the design of real-time logic for ASIC applications, but in C++. The advantage is by writing our code in C++, we can have that really quite fast turnaround time and access all sorts of debug tools available for C++ that might not be present for Verilog and so on. And one of those tools is Undo's time travel debugger, and that's what we're going to be having a look at today. So I'm going to present a couple of examples based around Accelera's example code that they provide. The first is fairly simple, just to give inspiration and to show how the theory works, and the second a bit more complicated, to go into a bit more depth of something complicated that's going on that we aren't familiar with. So let's get cracking. So I've run here make check on the Accelera examples, having already introduced a small bug that we're going to debug. And we can see when I've run this script, we can see there's a failure, and it's in this simple FIFO test.sh. So if we take a look in that test.sh script, we can see essentially it calls another program through this eval command, and that other program being simple FIFO test, which is this script. And this script is very long and ends up executing the program itself through an exec command. Now, this kind of wrapper-based technique is quite common, particularly in large companies with processes that have evolved over time. It can make it slightly more awkward to attach a debugger. It's actually not an issue with Live Recorder because there's an option to attach to a specific program. So let's fire up Live Recorder, and we're going to be using the record on argument and tell it to grab the program test, and then we give it this test script that we're looking for here. So let's kick that off. And what we can see is happening here is that it's going to firstly write a recording of the outer wrapper, and then make a recording of the program that we're actually interested in debugging. So it's this 164.undo log file that we're interested in. So we also need to understand a little bit about what's going wrong. So in this Accelera examples model, it's this test.sh.log that gives us the output, and we can see this is the output that we got, and this is what we wanted. So to our human eye, we can see that there's some kind of shift in the output, but really in terms of starting to debug, it's this initial character I, which should be a V, that we're going to bear in mind when we're debugging. So we have a recording. Let's load that up in Undo's debugger. So we're going to go to run and debug. This is using Visual Studio Code with Undo's extension installed. And here we need to make sure we're using UDB to replay a live recorder recording. We hit the play button, and this should pop up a window into which we can find this 164 recording. So that's just going to load up here, and we start to see some of the windows we'd expect for debugger loading. We have this bar at the top with some helpful icons to save us typing commands into the terminal window, that we can do that as well. We have a timeline here at the bottom, and we can see that we've attached to the debugger at the end, and we can also see it says end here in the terminal window. Just to note that if you're using a command line interface, sometimes it attaches at the start, so make sure you know where you are when you're starting to debug. Okay, so we need to get debugging. So let's have a look into the file where we output this text. So we have this simple FIFO, and we need to kind of work out firstly where our output. So it's C++, so a good starting point is cout. And sure enough, we can see here that it starts by outputting an end-line character and then does a loop of reading in characters and outputting those characters. So we'll set a breakpoint there by just clicking there. And we're at the end. Remember we look back in this log, we want to find out where our first character is going wrong. Let's give ourselves a little bit more space by dragging this window down. So what we do is by going back to the start, and we'll notice here this says start, the timeline says start. And now, having set this breakpoint here on this first C out, we can step forwards there. And sure enough, we hit the breakpoint and we see that C is set to I. So we want to find out where that came from. Now, what we could do is step back into this read function. And we'll see here, we see the data being set. Now that was quite easy. It gets us close enough to where we want in this example. There's a more powerful way of getting there. In case this had a whole hierarchy of events, we can click this here, this last changed button, and type in C, hit the return key, and that will take us to exactly the line where it's set. And remember, we're going backwards. So the old value is what it was set to after we would have executed this line. So we can close this little window here and we can take a look. So we see data. Within data, we can see VISIT. So we can see the V's there at slot 0, and we can see a couple of I's at slot 1 and slot 3. If we have a look at first, we can see it's 1. So we can see what's going on now. We're loading our first ever character, this I from slot 1, but not 0. So that's a bit curious. Why don't we load from the 0th element the first time? And sure enough, if we look at what the code's doing here, we'll see that we increment the first character and then we read the data. Well, that's the bug, isn't it? That's the wrong way around. We need to read the data first and then increment the first variable second. Okay, that was a very simple example just to give the inspiration. Whilst we're here, let's just take a look at the call stack, because that can be useful. It can be a bit confusing in systemc. So the way the systemc scheduler works is it rips out, in assembly language actually, the stack and everything for the process when it reschedules each of its threads internally. So what that means is that it can be quite hard to work out the sequencing events and how things happen. My suggestion is to actually not worry about that, to just set the breakpoints and use the last command to see where data was changed within your code itself, and leave all the scheduling to the scheduler itself. And in fact, that's what we want to do, because our scheduling may not be deterministic in certain use cases. And if we look here, we can see that sure enough, the bottom 4 parts of the call stack are systemc specific things, and then we get on to the stuff that we expect on the top. So just focusing on the top, setting our breakpoints, using last, that gets us most of the way. Okay, so we're going to run another example. So let's just clean up a little bit here. We click that square there to come out of the debug mode, and we can clear up these terminals. Okay, so we're now going to take a look at a second example. And this is something a bit more complicated. It's a simple bus example where there's many different things interacting through an arbiter. So the behavior might not be so deterministic. It might be really difficult to see where different pieces of data are coming from and going to. There's a bit more real world for us. And the kind of techniques I'm going to show here will be really useful if you're trying to debug a code base that you're not familiar with, or just if you want to understand what's going on. It might not be that there is a bug, but you need to understand why something's happening a certain way. So again, I've introduced a small error. We can see by looking at the output log file here that the first issue arises at 400 nanoseconds, where we see the data 26182C1C, but we're actually expecting 1B1DDE. So we can deduce that either the data that we're trying to read here was corrupted, or that we're reading from the wrong area. So we'll see what. So again, in the same kind of way, let's do a recording. This time a simple bus test. Just like before, we're going to see that's going to do 2 recordings, one from the outer and one from the inner. So it's this 357.undo that we're interested in. And if we scroll down just a tiny bit further here, we'll see, sure enough, something weird's starting to happen around 400 nanoseconds, and that's where we get the incorrect data that we saw in log file above. So let's attach our debugger to that recording. So we'll just let the window pop up. Go and find that recording, and this time again it's a 357 recording. So we can let that load up. And again, we need to go and find somewhere to attach initial breakpoints so we can see what's going on. So I've had a look through the code, and this time it's not cout, but it's a printf that's printing the data out. And you can see here we have the timestamp and the other similar elements in the same way. So what we want to try to do is reach the my data point when this timestamp is 400 nanoseconds. Now, that's not quite so simple this time. We don't just have a simple variable, we can set a breakpoint on here. So what we'll do, just set any old breakpoint, starting at the end of time, and we'll just play backwards until we hit that. Now we have to do a bit more work. We need to see what this could help us with. So if we look at system timestamp, and we can go to the definition and we can see that this SC timestamp returns timestamp element of the current sim context. Again, let's go to the definition of that, and can see that this SC cur sim context is likely to be the thing. So let's grab that. Can we see that? Yes, we can. Fantastic. So let's just go back up and then see what this timestamp returns. And it returns mcur time. So hopefully, if we again look at that, we can see something there, and it's got an m value. That's helpful, isn't it? So we can print that. Okay, that's something we can use now. We've got a timestamp. So let's now make this breakpoint we have here conditional. So we can edit it and we can add a condition. We want to stop at 400 nanoseconds. Now, if you dug a bit deeper, you'd find out that actually those timestamps are measured in picoseconds. So we need to actually set it on 400,000 picoseconds. So update that conditional watch point, and we'll play backwards until we hit it again. And if we take a look, we're now right back at the beginning. We've gone from 98% of the recording to 6%. And timeline window, we're near the beginning. It's looking more promising. 400,000, that's what we expect. And if we have a look at my data here, set to 38244C, which is the same in the hex. We can go and look at this in a memory view, which might help us to realize that. So remember, the error was 26182C, and we can see here 26182C1C. So we've found what we're looking for. So now we need to find out, where does this my data 0 getting set to the wrong data? So again, we're going to use the last command, and we'll just type in my data 0 here, and that's going to wind back to where it's set. So at this point, we can see that it's loading it from this memory and from an address. So there could be two things going wrong here. One could be that the memory is wrong. One could be that this address calculation is wrong. At this point in our debugging, we can't actually tell. We have to take a guess. So we'll remember that. We'll go down one of the debug rows, and if it's wrong, then we can come back and try the others. So let's, to start with, assume that the addressing is correct and the data is wrong. So if we copy that, and then I'm just going to show you how you can enter commands down in the terminal window down here as well. We can check that we can access that. That memory is 38, which is the incorrect data as we expected. So we can run last on that as well. And then this will just roll backwards to when that was set. And we can see it was set from something else to 38 decimal at this point. So again, we can close that, and we want to see where did that come from. So again, p star data, that's the 38 as we expect. Where did that come from? And now we're back out here, look, to where it looks like it's been set up in the first place. So this is the point in our debugging where we're going to actually have to start understanding what the code is doing. So click that to make it permanent. So let's have a look. This is the main action in bust master blocking. So it's doing a loop, waiting for clock edge, then it reads a burst of data, and then we're operating on the data, waiting for a clock edge, then we're writing out a burst and waiting for the output. So if we went and looked a bit in the documentation about this burst read, what we'd find it's doing is every clock edge expects the data to come back sequentially. What we're actually doing here is operating on all the data as though it was back in one pulse, which means that we're going to start operating pretty quickly on corrupt data. And we can see here I is 11. So we're somewhere through that into the 11th element here, and we're setting it perhaps to the wrong value, or because we're doing a plus equals here. So we're actually reading the wrong value because we've read it before it's been updated by this burst read. So what we actually need to do is do all of the waiting before we update the data. Or better still, we could do what the code initially did, which is just to simply put this wait into the loop like this. If it will play ball with us, there we go. Put the wait into the loop, if you excuse the indentation. And this is probably what the ideal code would look like, because what we're telling the further synthesis tools is that we need to wait for one element to be ready, and then we can operate on it, so that it will help the synthesis tool to learn that it can do a pipeline. So hopefully that should give an idea of how, in this quite complicated example, we didn't care about all these other places that we're reading, writing. We just dived straight down by using the last command to see the issue that we had. So there's a couple of tips I'm just like to add before we wrap up this video. Firstly, if we think about debuggability when we're designing. So firstly, intermediates. Remember here we had to unwind this a bit, and we were lucky that we could find that timestamp as a value that we could set the conditional breakpoint on. It would be helpful if that was there as an intermediate already, and then we wouldn't have to go and unravel all of that each time we wanted to do some debug if we'd thought about that up front. The second thing which would be even more helpful, if rather than this checking happening in a log afterwards by comparing the output with an expected output, if that checking could have happened somehow here, say by reading in a known good result file, doing a comparison here and asserting if there's a failure, then of course we could immediately set the breakpoint on assertion, so that'd be much faster. And the final thing I wanted to mention is with our test frameworks, and particularly with regression runs, is that live record can be really helpful here. So this live record also has a retry for command line argument. And what it means is, say we run our regression tests and there's a couple of failures, we can then tell it to rerun immediately to try to capture a log of that failure or a recording of that failure. If something's deterministic, we might always need to run with the recording turned on to make sure we catch those failures. But what it can mean then is the next day we can come in and immediately start debugging. We don't have to worry about trying to synchronize our trees, rebuild at exactly the same moment, run with the same seed. We have a recording there that's just there to run, and so that makes this really fast. So I hope that was useful. Thank you for your attention. If you have any other tips of how to use time travel debugging effectively with SystemC, we'd love to hear about them. Please give us the feedback through the contact us section of the Undo website. Thanks for listening.